Hello students, so continuing our lectures on electronic devices. Uh, we'll discuss about PN junction here. So suppose a PN junction is formed of germanium PN junction, and the depletion width of that PN junction, that is WD, is say 1.5 micrometers. The donor concentration is 2 into 10 to the power 15 per centimeter cube, and the acceptor concentration is 5 into 10 to the power 14 per centimeter cube. Now somebody asks you to find out the width of the P junction. So from the relationship, that is Wn, width of the N junction into the donor concentration, is equal to the width of the P junction into the acceptor concentration. So if that is the case, then we can write Wn by Wp is equal to Na by Nd. So if we add these things, so we know this value, so we put plus 1 in both these cases, and it turns out to be Wn plus Wp by Wp is equal to Na plus Nd by Nt, and this is nothing but the Wd. So we can write Wd Wd by Wp is equal to Na plus Nd by Nd. So in that case, Wp by Wd is equal to Nd by Na plus Nd. So Wp is equal to Wp into Nd divided by Na plus Nd. So we put the values. Wp is 1.5 micrometers, and Nd is 2 into 10 to the power 15 per centimeter cube, and it is divided by Na plus Nd. So Na plus Nd, where Na is 5 into 10 to the power 14 per centimeter cube, and Nd again is 2 into 10 to the power 15 per centimeter cube. So if we evaluate, if our value comes out to be equal to 1.2 micrometer, this is the width of the depletion region in the P site. So the next problem that we will discuss is what happens when we increase the built-in potential for an homojunction p-n junction. So when we have a p-n junction, which is a homojunction, that means the material on both p and n side are same. are increasing the built-in potential. V0. So if you have three type materials, for example, we have germanium, we have silicon, and we have gallium arsenide. We need to find out what will be the built-in potential in these three cases, and what is the hierarchy of the built-in potential. Now, a built-in potential or a contact potential. So built-in contact potential is given as VO, which is equal to KT by E log NA ND by Ni square. Now, if we assume that the dopant concentration is constant, and if we assume that the dopant concentration are same, at all the junctions, at room temperature, so this one becomes a constant. Na and NT becomes a constant, and this one is also a constant. So we are only left with V0 is equal is now proportional to log of 1 by Ni square. So higher is the intrinsic carrier concentration, the lower will be the built-in potential. So in the case of gallium arsenide, the intrinsic carrier concentration is 2.4 into 10 to the power 6 per centimeter cube. In case of silicon, it is a little higher, 10 to the power 10 per centimeter cube. Whereas in the case of germanium, it is 2.3, much higher, 10 to the power 13 per centimeter cube. So you can see that germanium among the three has got the highest intrinsic carrier concentration, and the gallium arsenide has got the lowest intrinsic carrier concentration. So that implies that the built-in potential of germanium will be the lowest of the three, and it will be less than the built-in potential of silicon, which will be even less than the built-in potential or the contact potential of gallium arsenide. Next is, if in a p-n junction, that is JPN made out of silicon, if the doping concentration in the N region is much higher than the doping concentration in the P region. So doping concentration in N region is much higher than the P region. That means in case of p-n junction, we can call it a p-n plus junction, the higher doping concentration here. Then the depletion region lies almostly inside the P region. So if that is the case, then we know that the doping concentration in the N regions, when we will talk about the donor concentration is much higher than the accepted concentration. So from the relationship WPNA and WNND is equal to WPNA. So that means Wn by Wp is equal to Na by Nd. So if Na is much less than Nd, or Nd is much greater than Na, so it will imply that Wp is much greater than Wn. So that means the depletion region will almost lie entirely in the P site. The next problem is in a silicon junction transistor. If the accepted concentration is 10 to the power 15 per centimeter cube, and the donor concentration is 5 into 10 to the power 16 per centimeter cube, and the intrinsic carrier concentration is 10 to the power 10 per centimeter cube. Then the built-in or contact potential that is V0 is equal to kT by E, and it is again ln nd Na by Ni square, and so we put the values, it turns out to be 0.7 volts. And if somebody tells you to find out the depletion width, total depletion width, that is WD, so total depletion width is again given as 2 epsilon 0 epsilon R V0 into Na plus Nd divided by E NaNd. So that gives you the value 0.97 micrometers.